Hello everyone, my name is Aksharaa and my friend Nithin. Today we are going to talk about how many ways and times have we to shuffle a deck of cards to create maximum randomness. Generally, shuffling is a basic step of playing any card game. As we know that we create randomness by either shuffling or by cutting and creating randomness. Shuffling is a basic process of shuffling the cards from top to bottom or from bottom to top, whereas cutting involves cutting the deck of pack into two and interleaving each other, which also creates randomness. A basic example of shuffling is a topping shuffling. In topping shuffling, we take the topmost card of a deck of n cards and place it in any of the n minus 1 cards and repeat the cycle, which creates randomness. An example could be given with 3 cards, taking in the natural order 1, 2, 3. So here we consider the order 1, 2, 3, 3 cards, which are 1, 2, 3, to be cut into 2 deck of cards, taking one deck of cards in one hand and the other deck of cards into other hand. Considering 0 to be the first card and considering the probability of this card would be 1 by 8, and the possible interleaving would be 1, 2, 3, which is a natural order. When we cut the first card and take the next 2 cards as another deck of cards and try to interleave them, we would end up with the possible interleavings of 1, 2, 3, 2, 1, 3 and 2, 3, 1, and the same process repeats for having 1, 2 as a deck and a 3 as another deck, or having 1, 2, 3 as a single deck and having none on the other hand. So adding of all these probabilities would be 1. So in this case, adding of all these probabilities is given as 1 by 2, and the permutations are given as below. Here we should consider an important distinction between ordering and permutation. Ordering is a specific way in which cards are ordered. Permutations or arrangement is not independent on order. So coming to the riffle shuffling. Riffle shuffling is a basic way of cutting the cards and then creating randomness. Here in this riffle shuffling, the pack of n cards are cut into 2 and the deck of cards are independent of the packet size, which means that the packet size will not influence in any way for the shuffling, and these 2 cards are then interleaved among each other, which creates randomness. Another important concept in shuffling cards is the rising sequences. This is also called as a magician's trick. With the help of rising sequences, one could be easily fooled. This can be explained with an example considering an 8 card deck in the natural order, which is like 1, 2, 3, 4, 5, 6, 7, 8. After doing a particular shuffles, consider here as 2 shuffles. After doing 2 shuffles, we would be left with 2 rising sequences, which is given as 1, 6, 2, 3, 7, 8, 4, 5. Here 1, 2, 3, 4, 5 is considered one sequence, and 6, 7, 8 is another rising sequence. Here, if the magician asked us to pick one of card without him noticing what the card is and rearrange its position, the magician would know what the number is, because he would obviously know what are the rising sequences of the given deck of cards. So this is a very important concept in card shuffling. Coming to A shuffles. A shuffling is very important here. The logic lies behind cutting the deck into a number of different packs, and here the size of each packet does not have any influence on the shuffling or creating the randomness. The probability of each particular packet is given by the binomial distribution of the number of cards n and the probability of each packet of cards, which is divided by number of packets the deck of cards are divided into. Here these 2 equations shows that the probability is nowhere dependent on the size of the packets, but is always dependent upon the number of packets. And an example of this could be explained with the given code, which is A equal to 23004103. This is a code for the 5 shuffle of 8 deck card. So there are 3 ones, 1 1, 1 2, 2 3s, and 1 4, which gives us as the probability of P1 is 3, P2 is 1, P3 is 1, P4 which is equals to 2, P5 equal to 1. So the deck of 1 2 3 4 5 6 7 is now cut as given P1 equals to 3, which indicates number 1 2 3 in one deck. So this cycle repeats, and when we get a when we do the shuffling, the final shuffle deck would be 5 6 1 2 8 4 3 7, where this is where 1 2 3 4 5 6 is the natural order. And the next will be continued by my friend Nithin Shekhar.
Good afternoon everyone, my name is Nithin. I'm going to discuss about this multiplication theorem. Initially we have studied about this riffle shuffle, A shuffle and top-in shuffle. I'm going to discuss more about this A shuffle now. So what does this mean? The multiplication theorem states an A shuffle followed by a B shuffle is equivalent to a single AB shuffle. So suppose if we consider a deck of cards and shuffle it according to the permutation A, which is mentioned here, like this is an example. Consider this A permutation and a B permutation, and individually when we shuffle these cards according to the A and B, so we get the order as mentioned here. So when we convolute these two results, we get a specific result. Suppose if we take these two permutations and do bitwise concatenation such that we get a new result of per new permutation. When we shuffle the deck of cards according to this permutation, we get a result. So when we compare these two results, they're almost same. So this theorem states that these two processes will give exactly the same resulting probability density on this set of permutations. So hence an A shuffle followed by an B shuffle will be equal to single AB shuffle. Previously we have covered the rising sequences. My project partner Aksharaa has covered these rising sequences, about how to find these and what exactly these rising sequences are. So right now I'm not going into detail of rising sequences, but I'm going to mention how these rising sequences are useful in order to find the variation distance, such that in turn we can find out how randomly these the cards have been shuffled. I mean how close these shuffled cards are to the randomness. So this is the formula mentioned here in order to find the number of rising sequences. So where A refers to number of shuffles and N is a deck of cards. So coming to the variation distance, previously we have discussed about how this variation distance can be useful in order to find how close this shuffled deck of cards are to the randomness. So as we see here, we are finding the difference between the two probability densities. So this R power k to the pi refers, it is the probability density obtained after a riffle shuffle of k number of times using the pi permutation, whereas the u power of pi is complete reversal of the R power k of pi. U of pi is nothing but the deck shuffle it's completely deshuffled cards, nothing but these deck of cards are in the natural order, and not even a single card is shuffled in this deck of cards. When we take the difference of these two probability densities, so we get a specific value, and when we compare this value to either 1 or 0, we see the value range or the closeness to 0 or 1. If the value is more closer to 0, we can conclude that the shuffle deck of cards is much more near to the randomness. So using the computer simulations, we carried out an experiment in order to calculate the variation distance. So we considered the 52 deck card, and when we did the shuffling, for so many times, so we found 10 power 68 rising sequences. So when we plot a graph based upon this result, when the k was at 7, the number of shuffles were 7, we saw a very good point, the curve. So which we concluded by seeing which we concluded that 7 number of shuffles are sufficient in order to shuffle a deck of 52 cards, which gives a very good value. And the shuffle deck of cards were very close to the 0, which means that it is much more randomized and it is close to 0. Coming to this inverse shuffle, so basically inverse shuffle is nothing but deshuffling of the shuffled cards. When we shuffle the cards using some permutation, suppose in the example we have given 12202011110, we have shuffled the cards according to this permutation, and we obtained a shuffle deck of cards which is given below, which is 478192563. So when we take all these shuffle deck of cards, so we can use this method. So this method suggests that you have to take all the zeros back from this shuffle deck of cards, which is 0 and which corresponds to the cards here. It's 1 2 3. We can take these cards and place it on the table, and then we consider ones from this code. We take all the ones, which is 4 5 6, and we take them and place beside the zeros, and then we take the twos. So we take the twos, which is 7 8 and 9, so we place it here. So when we look at the complete set, we see the deck of cards have been rearranged to the natural order. So this is a very useful method in order to deshuffle the deck of cards. So Peter Doyle was a person where he invented a game in order to shuffle the deck of cards. So initially we shuffled the 52 deck of cards, like 7 times we shuffled them, and we got a value around 0.884, which was pretty much not that close to 0, but it was a very good value when shuffles were 7. Peter Doyle invented a method where he took a deck of 52 cards, he turned face down, and then he labeled them in this order. Now he did the riffle shuffle 7 times. Then he dealt cards from one time from top to top of the deck. So when one comes up, he placed it face up on the table and he called it as pile A. And if the 27 comes up, he placed it face up on the table in separate pile, calling this B. And if any other card comes up, it is not in the intermediate successor of the top card in either A or B, then he placed it face up in the pile C. So if the immediate successor of the top card of A comes up, he placed it face up on the table on A, and then same for B. He went through the whole deck this way. When the process was done, so he picked up the C pile and he turned it face down, and he repeated the procedure, and he did this for all the third set of deck cards. And at the end of the game, we can see either a pile A or pile B is full, and each has 26 cards in it. So when we tried to find these rising sequences from the first half and the second half, what we saw was the rising sequences more are in the forward direction and in the first set, and when we saw the rising sequences in the set B, we saw that the rising sequences were in the backward direction, and the number of rising sequences in the pile A were much more in the number than in the rising sequences in the pile B. And also it is more faster to get these longer rising sequences into A than it is into B. So we found out the probability densities and found the probability difference. We found it was 0.31, which was far better than the result which we obtained in the previous computer simulation of 52 deck of cards. Since this value was very close to 0, and this method makes a shuffle deck of cards very close to the random. So In order to conclude, this game was not fair because when we are trying to arrange these deck of cards into pile A and pile B, what happened was, uh, in the computer simulations, for every 80% of the time, what we observed was pile A was getting filled up in um, much more sooner than the pile B. And the number of cards in the pile A had many more rising sequences than in pile B, and because it is more easier to occur the forward rising sequences than the backward rising sequences. So this was not a fair game. So just a to just for a point of having very good variation distance, the game is very useful rather than considering it for a fair game. So we can move on to the Markov chains. So previously we have learned about the Markov chains, where it defines of having a set of states, and for a process, in order to move from one state to one more state, uh, it doesn't have to depend on all other states but except the current state. The current state will be depending on the previous state. Suppose we have set of states from S1 to Sn. The process starts in one of these states and moves successfully from one state to another, and each move will be called as a step. Like if chain is currently in the state 1, then it will move to state 2, and the next step with the probability of p of 1 2, and this probability does not depend upon the states which chain was in before than the current, as I said earlier. Then this probability of p of 1 of 2 will be called as the transition probability, and this process can remain in the state, and this state it is, and this occurs with the probability of p1. And also we have this initial probability distribution which can be defined as S, and it defines the starting value. Usually we can do this by specifying a particular state of the starting state. So we can apply these concepts in order to the shuffling concepts. So we can find the transition probability of p pi of tau will be is the transition probability. Like if we have two permutations pi and tau, if we try applying these permutations to the deck of cards, we obtain particular order of shuffled cards. So we can find the probability of going from particular shuffled order to a different shuffled order which were obtained by pi and tau. We can find the probability by using the formula. Considering this example which was covered in the initial slides, we can take the same example, and also using the formula which we defined in the previous slide, we can find out all the transition probabilities and can place them in the transition matrix. Now considering the initial density as 1, which is a state 1, so considering a unshuffled deck of cards, which are the cards in the natural order, so when we do the riffle shuffle, like the shuffling here will be denoted as the power, where if like if a p is a matrix, then p power 2 represents the 2 shuffles, if p power 3 represents the 3 shuffles. So when we calculate all the transition probabilities, we find this transition matrix. So when we perform the shuffles, after certain amount of shuffles, the values in this matrix remain the same. As we can see here, the values are more closer to 0 rather than 1. So utilizing Markov chains, we can find the variation we can find the values which are more closer to 0. So this method proves to be more beneficial than using the variation distance, as we covered in the previous slides. So in order to conclude, it is clear that 7 number of shuffles of the 3 card deck gets up very close to the uniform density, and which turns out with the stationary density, And we must also note that mark or change for riffle shuffling or the regular, that is there is some number of shuffles which any permutation has a positive probability of being achieved. So once we obtain a transition matrix of certain values after certain shuffles, if we try to shuffle them more, the values won't change. The values in the column or the rows will remain same after certain number of shuffles. So for the 52 deck of cards, we found the 7 number of shuffles were very useful. So thank you so much for your time. If you have any questions, you can email me the questions. I can reply you through those emails. Thank you so much.